Hey there! Let's talk about something that's, well, at the very heart of statistics and data science, something called the random variable. It sounds complicated, but really, it's just a clever tool that lets us take something messy, like pure chance, and turn it into clean numbers we can actually work with.
I mean, think about it. You flip a coin, heads or tails. Super simple, right? But what if I asked you, what are the odds of getting exactly 6 heads if you flip that coin 10 times? Or at least 8? All of a sudden, that simple little coin toss gets way more complicated. And to get from that one simple flip to a complex probability, you need a special tool.
And to really get why this tool is so important, just think about the difference here. A random process, like flipping a fair coin, has uncertainty baked right in. You never know for sure what's coming next. But a deterministic process, like flipping a coin with 2 heads, that's totally predictable. You get heads every single time. The whole goal here is to find a way to manage, to measure, and to make sense of all that randomness. So how do we do it? How do we wrestle with randomness? Well, statisticians came up with this absolutely brilliant idea, a way to translate these uncertain real-world events into cold, hard numbers. You can almost think of it like a machine, a random variable machine. Okay, so what is a random variable, officially? The key thing to understand is that it's not the outcome itself. It's not the heads or the tails. No, it's actually a function. Think of it like a rule that assigns a number to every possible thing that can happen. It's like the official translator between our messy, unpredictable world and the clean, orderly world of math. Let's go back to that machine idea. You feed in an outcome, say heads, and whir, click, it spits out a number like 1. You feed in tails and it spits out 0. That machine, that rule you just made up, that is your random variable. It's the thing that makes randomness something we can finally count, calculate, and analyze. Let's make this real with our coin flip example. Step 1, the experiment. We flip a coin 10 times. Step 2, we define our random variable. We'll call it big X, and we'll say big X equals the total number of heads we get. And finally, step 3, we actually do it. We run the experiment and get an outcome. Let's say we got 6 heads. That number, 6, is what we call a realization. See the difference? Big X is the idea, the rule. Little x, our 6, is the actual number we saw.
All right, so we can turn outcomes into numbers. Great. But as it turns out, these numbers come in 2 very different flavors, and that changes how we have to work with them.
The 2 types are discrete and continuous. Discrete variables are things you can count. Think distinct, separate values, like the numbers on a die. 1, 2, 3, 4, 5, 6. You can list every single possibility. But continuous variables are totally different. They can take on any value inside a range. That means between any 2 possible points, there are infinite other possibilities. So our coin flip example, that's discrete. The number of heads can be 0 or 1 or 2, all the way up to 10. You can't get 2.5 heads, right? But now, picture a spinner on a clock face. Where could it land? It could be at 3 seconds, or 3.1 seconds, or 3.14159. The number of possible stopping points is literally infinite. That, my friends, is a continuous variable. So now that we know there are these 2 different types of variables, the next big question is, how do we actually describe the probabilities for them? As you might guess, the rulebook is a little different for each one. For our discrete variables, we use something called a probability mass function, or PMF. And it pretty much does exactly what the name suggests. It tells you the mass, the exact chunk of probability, for each and every possible outcome. A PMF is what gives us the answer to, what's the probability of getting exactly 5 heads? And here it is, visually. This is the PMF for our 10 coin flips. See how the probability is highest right there in the middle, at 5 heads? That just makes sense, right? And as you move out toward the edges, getting 0 heads or all 10 heads, the probability gets way, way lower. Each one of these bars shows you the precise probability for that specific outcome. But for continuous variables, that whole approach just breaks down. Because there's an infinite number of points, the probability of landing on exactly one specific point is basically 0. So instead, we use a probability density function, or PDF. A PDF doesn't give you the probability of a single point, it shows you the density of probability around it. This lets us figure out the probability of an outcome falling inside a certain range. So here, for example,
The PDF for the average of 5 spins on our clock shows where the results are most likely to bunch up. To find the probability that our average spin lands between, say, 4 and 8, we'd actually measure the area under the curve in that zone. You can see the density is highest right around the center, at 6. So, we've got these maps of probability, the PMF and the PDF. But staring at a whole graph can be a lot. A lot of times we just want the highlights. And it turns out we can often summarize an entire distribution with just a few key numbers that describe its most important features. We usually focus on 3 main things. First, where's the center? This tells us the typical or average outcome, and we call that the expected value. Second, what's the spread? This measures how varied or predictable the outcomes are. We use variance for that. And third, what's the shape? Is the distribution nice and symmetric, or is it kind of lopsided? That lopsidedness is called skewness.
Let's start with the center. The expected value is easily one of the most important ideas in all of probability. It's not necessarily the single most likely thing to happen, but it is the average result you'd get if you could run your experiment over and over and over an infinite number of times. You can think of it as the balancing point, the center of gravity for the whole distribution.
And to make that super concrete, let's go back to our coin flips. If you flip a fair coin 10 times, the expected value, that long-run average, is exactly 5 heads, which, just feels right. Over the long haul, you'd expect about half the flips to be heads. Next up, we measure the spread with variance. This basically tells us how much the outcomes tend to wander away from that expected center. Think of it like this. Rolling a regular die has a higher variance than flipping a coin because the outcomes are more spread out. It's less predictable than a simple heads or tails. So low variance means predictable, high variance means more uncertainty. And finally, we look at the shape. Our coin flip example is perfectly symmetrical, but lots of things in the real world aren't. They can be lopsided or skewed. A classic example is income in a country. Most people are clustered down at the lower end, but there's this long tail of a few people who earn a whole lot more. That lopsidedness, that asymmetry, is skewness, and it tells us a ton about the data. Okay, let's pull all these pieces together. Why do we go through all this trouble? Defining variables, functions, centers, and spreads? What's the point?
The point is that these are the fundamental building blocks we use to model our incredibly complex and uncertain world. Seriously, everything from predicting the stock market to testing a new medicine to modeling climate change, it all starts right here. By taking something as wild as pure chance and describing it with numbers, giving it a center, a spread, and a shape, we can start to understand it, predict it, and make much better decisions.
In the end, random variables don't make uncertainty disappear. What they do is give us a language to talk about it, to describe it, to quantify it. And that is an unbelievably powerful thing. It lets us measure the unknown, which leaves us with one last fascinating question. Now that we've learned how to measure uncertainty, can we ever truly get rid of it?